sometimes we need to solve an equation, but we can't do the answer through algebra, in which case we'll need a numerical method for doing that. So for example, we have this curve here, and let's pretend we want to find where it crosses the x-axis, but there's nothing that we can do with algebra that will find the exact answer for us. If that's the case, we're going to need to approximate the answer. So one idea is to start with a guess nearby, and then use the linearization to get a better guess. So if we started, say, at 2 here, and we drew in the tangent line, which would be the linearization, we could follow that tangent line back to a better guess. Then we could repeat that procedure. You can see after the second time, it looks like we're getting a very, very good estimate by taking that tangent line and following it back. Looks like we're getting a very good estimate for the zeros. We could continue to get better by zooming in here. So zoom in, you can see, ooh, this tangent line is still pretty close. Let me zoom in one more time. Okay, so our second tangent line had brought us to this point, and then we would come up to the graph, find the tangent line. At this point, the graph is so straight that the tangent line is almost exactly the same as the graph. You can see that's going to very quickly take us very close to the actual solution of the problem. Okay, now when we really do this, we're not going to take time to draw graphs. What we want to do is to come up with some iterative or repeated scheme for getting these better and better answers. But the graphs help us figure out what to do. So let's go back here. Let's think about this as being our current guess. So I'm going to call that x sub I. This I is a little subscript to indicate this is my ith guess. Now what I want to do, I have this function, and I want to find the equation of the tangent line. I want to find the linearization, in other words. Remember that the formula for the linearization is that linearization is equal to the value of f at the point, which in this case would be f of xi, plus the slope of the function at that point times x minus xi. Now what I want to do to get my next guess is to figure out where this is the equation of the tangent line, the equation of the linearization. So what I want to do is to figure out where does that tangent line cross here. That'll be my next guess. I'll call that x sub I plus 1. I plus 1 so that I'm sort of adding 1 to the name each time because I'm getting better and better guesses. So to do that, I've got to figure out where does this tangent line cross the x-axis. So I want to find the particular value of x that I should put in here, which I'm going to call x sub I plus 1, so that I'll get 0 out. So to solve here, I'm going to have to subtract f of xi from both sides. So I'll have f prime at xi times x sub I plus 1 minus x sub I equals negative f of x sub I. Now I'm going to divide by the derivative, so that on the left side I'll just have the difference between my next guess and my current guess, and over on the right hand side I'll have the value of the function at my current guess divided by the derivative of my function at my current guess. Finally, I'll add my current guess over here, and I'll see I can find my next guess by taking my current guess and subtracting f at my current guess divided by the derivative of my current guess. So I'm going to start with some guess. I'm going to calculate this number. That will give me my second guess. Basically what's happening, we set it up so that I was starting with this value, and then I was following the tangent line back to where it crossed the x-axis, and that should be, hopefully, closer to the 0, to the solution where this function crosses the x-axis. So I should get closer and closer to the solution of the problem. So if I go far enough, then I'm hoping that f of, by the time I've taken several guesses here, I'm hoping that I'll be very, very close to 0, right, so that I have a really good guess. Let's look at an example of how this formula would work. By the way, this formula is called Newton's method. So this is the formula we got. Let's use Newton's method to find where 5 minus x and e to the x cross. Now, what we want to do then, we want to solve this equation. Where does 5 minus x equal e to the x? But remember, the way we set up Newton's method, we need to be finding a place where some function is equal to 0. So let me rearrange this a little bit. Solving this equation would be the same as finding out where does e to the x plus x minus 5 equal 0. Once we have it in the form of f of x equals 0, then we can apply Newton's method. Okay, so in this particular case, f of x is e to the x plus x minus 5. So the derivative would be e to the x plus 1. So putting that into Newton's method, it says that my next guess should be my current guess minus the function at my current guess divided by the derivative at my current guess. That would be e to the xi plus 1. There we go. All right. So let's see. Let's actually try this. So we could do it by hand, but the idea is to have a computer do the computations for us. We just know that if the computer keeps computing this thing with my next guess and my next guess and my next guess, it'll keep getting better and better approximations. Let me show you how to just use like a simple spreadsheet like Excel to do that. So I've got Excel here, and we've got our formula. Now we're going to put our first guess in this cell. So I'll just guess 1, since I haven't really looked at this function. I don't really know exactly where the solution might be, but I'll try that guess. Now, what the formula says is that I should take my next guess and then subtract this thing evaluated at that current guess. So I should take my current guess and subtract this function evaluated at my current guess. Now, in a spreadsheet like Excel, to put in a formula, you always start with an equal sign. So I've got an equal sign here. And then I can reference the number above just by looking at the row and the column that number's in. This one is in row 1, column B. So I'll type in B1. That will automatically go up to that column, to that cell, and grab that number. Now I need to subtract this fraction. So I'll put the numerator and denominator in parentheses. I need to take e to that number. I need to add that number, and I need to subtract 5. I need to subtract 5 in the numerator. Now in the denominator, I need to take e to that number, which is stored in cell B1, plus 1. Okay, and then divide. So this gives me my next guess. Now the cool thing about a spreadsheet is that if you paste a cell down, it will automatically update the references. So I'm going to copy this. So Control C is how you copy, Control, and then go down to the next cell and hit Control V to paste it. Now the cool thing about Excel is that it automatically updates the cell references. So remember before, when we looked at this formula, you can hit F2 to see the formula, or you can see it up here in the formula bar. Before, when we typed in this formula, it was referring to cell B1, but since I copied it one cell lower, it automatically lowered this to cell B2 so that it continues to look in the same relative location. That's called relative referencing. By the way, if you don't want the relative referencing, then you put a string in front of the item. So like if I didn't want it to update the cell number, I'd put the $sign in front there. And this time when I copied it, that would remain B2 even though the other one's updated to B3. So I don't want that. I like the relative referencing. You see what's happening each time the formula we're applying the same formula to the next guess. So I'm just getting a list of guesses here. As I keep pasting them down, notice that the guesses have converged to the answer. So we've found the solution of this equation. Well, we found an approximation to it. So you can see that that approximation appears to be accurate back quite a few decimal places. 1, 2, 3, 4, 5, 6, 7, 8. It's good to 9 decimal places and maybe even more. That's all that Excel happens to be displaying to me. So with Newton's method, what we do is we start with a guess and we keep applying the same formula to those guesses, keep following the tangent lines back until it looks like we've converged. It was actually pretty quick. We haven't had many changes since we got to our 6th guess. So if you're going to write a computer program to do this, you would each time have it compare the next value to the value that came before. Once that change is too small for you to notice, then you can stop. Let's do another example. We want to use Newton's method to get a procedure for finding the square root of any positive number. Okay, so this takes a little bit of work, but I want to be able to figure out what the square root of some number is. Now, what we probably want to do is to try to do it without having to use any built-in square root function. So if I square both sides, I'm looking for the number whose square is a, and for Newton's method it needs to be in the form some function set equal to 0. So that's what, if we're trying to figure out the square root, we're actually trying to figure out when does x squared minus the given number equal 0. Now the derivative of this function would be 2x. So according to Newton's method, to get our next guess, we should take our current guess and subtract our function, which is x squared minus a, our function evaluated at the current guess, divided by the derivative at the current guess. Now I could actually simplify this a little bit. If I got a common denominator, I would need to multiply this top and bottom by 2xi. So I'd get 2xi squared over 2xi minus, now the denominator is common, I would have minus xi squared plus a. So I really have 2xi squared minus xi squared is xi squared plus a all over 2xi. Or maybe it might be easier just to split this up. Let's see. We have, if I break it up into two fractions, xi squared over 2xi would be 1/2 xi, and then we have plus a over 2xi, whatever a happens to be. Let's show how we could use this to find the square root, say, of 2. So for 2, our formula is that our next guess is going to be 1/2 xi plus a. In this case, we're trying to find the square root of 2 over 2xi. Okay, let's program that in Excel here. So maybe I'll clean this off here. Okay, so our first guess, maybe we'll just guess 1 as our first guess. Remember, our formula says that our next guess, there we go, the formula says that our next guess should be the current guess over 2 plus 2 divided by 2 times the current guess. So I have my cell references there. So our next guess is 1.5. Then we get 1.41 and 1.414. And the beauty of this, now you can see we've converged at least to 9 decimal places so far. So actually that happened in about, well, we've applied the procedure 4 times at this point, and then after that it doesn't seem to be changing, at least not to 9 decimal places. So if we're happy with that accuracy, we could have stopped right here. Okay, so the beauty of this is we just calculate a square root, and all we had to have was multiplication, addition, and division in order to do it. And we could also set this up to calculate cube roots or fifth. Let's see. Oh, we set it up to calculate cube roots or fifth roots and so on. We could also set it up to calculate the square root of any function. What we would need is a cell that would hold our value of a. So let's say we want a to be so let's say we're going to have a be in here. So maybe we'll set it up with 3 as the value for a. I just have that stored in this cell. Now, the way the formula would change is just looking at the formula up top here. That's where a should go. Now I've got a stored in cell D1, so I'm going to use the dollar signs here. So string D, string 1. Okay. Now notice when I paste that down, it still references D1, right? Because I use the absolute references by putting the dollar signs in front of the name of the column and in front of the name of the row. So now let me paste that down a little ways, and we've gotten it to converge. So now setting it up this way, I could find the square root of any number. Let's see, square root of 4 will be 2, square root of 5, square root of 6. So it just automatically updates all the cells when I change that. So see, it's usually only taking 5 or 6 guesses for this to converge.